Thank you for coming to this talk. And there's some nice lead-up talks to this. One of the slides the previous speaker showed was debugging live apps. So that's what I'm going to be talking about. And Jeff Rush gave a really nice introduction to debugging. So I have a few slides on debugging that I'm going to skip over very quickly because he gave a really nice job of that and explained some of the problems that he mentioned that I'll be addressing in this talk. And there'll be several movie references in this talk. This is the first one. If you're a Python aficionado, you probably have seen it. And so this talks about the holy grail of debugging, what the ideal debugger would be. And you can learn a lot about that by watching science fiction movies. We'll discuss that as we go along. And this shows, for those of you who haven't seen Monty Python and the Holy Grail, this is, you actually have to see it to appreciate the Black Knight episode. I'm not going to, it'll take about 5 minutes to describe what it is, but it's really like a persistent bug that just never goes away, okay? It's a really nice example of that. I'm not going to waste 5 minutes showing the clip, but go ahead, go back and see the Holy Grail if you haven't seen it. Speak up? Okay. Oh, is it better? Yes. Okay. So we start with the project and myself. That's my name, Saravanan. I go by my last name. And there's a web page that describes this project. It's called OTrace. And if you Google for OTrace, in the first page, you'll see a link to this. So if you don't remember anything, just remember OTrace. The name OTrace is inspired by dtrace. Some of you may know dtrace. It's dynamic tracing of the operating system. So this is actually object tracing. That's why it's called OTrace. So you can do it in a live application. It doesn't have to be run only in a debugging mode, because zero overhead until you actually turn it on. So about myself, I teach meteorology here at Texas A&M, and I do research on climate modeling using supercomputers. And I worked on open source for many years, and some of my other projects deal with climate modeling. And I gave a talk earlier this morning about a graphical terminal interface. And there's some connection between that and this, because the debugger I'm talking about will actually use that as a graphical interface, but we won't get into that till the end of the talk. If you missed that, you could see the video of that. Python, I'm not very experienced in Python. I only used it for 2 to 3 years, but my philosophy is that if you don't know something well, you do foolish things. And what I'm going to do now may seem foolish, but once you know things very well, you don't do foolish things anymore. But you can decide for yourself if it's foolish or not. I'm working on a classroom interaction project, and that's how this got started. I use Tornado Web Server to do that. And debugging an asynchronous web server with a debugger can be a real nightmare. I mean, you can't step through an asynchronous web server. It just doesn't work, because there are like 100 requests happening simultaneously, and you just can't do that. So that's where this got started. Okay, as I said, I'm going to skip over this very quickly. Standard debugging, printf, putting print statements in the right place. There are various debuggers. You can set breakpoints, and you can do it printing, debugging, or postmortem analysis. You can do logging. Again, it was covered in the previous talk. You can do debuggers and exception tracebacks. All that was covered. So I'm just going to skip over it quickly. And the extra time I have, what I'm going to do is do foolish things like a live demo, which may or may not work. But we'll try that. But there's enough material in the slides in case that doesn't work. There are different ways to launch a debugger. You can launch it before the program starts. You can launch it after an exception occurs, there's postmortem. And you can invoke it within the program, and Jeff Rush's talk covered that as well. So you can invoke it within the code. You can put an if statement to make sure it's invoked when needed. You can set breakpoints. You can do line-by-line execution. You can do view variables, the call stack, and execute commands that modify variables. So you can do all that in a debugger. That's traditional. One thing which I like to popularize in a web application, there's a module called CGITB, which is very useful. So it produces a nicely formatted trace dump. So if you don't use it already or use an equivalent, you should consider using it. It's much better than looking at trace output. It just looks nicer. So the module is called CGITB. It's a standard Python module. OK, now we get into project OTrace. So debugging is like time travel. You want to go back in time to find out where the error occurred. So if you've seen Back to the Future, this is what's an example of a buggy future. And the good guys have become bad guys, and Doc Brown is in jail because something happened in the past and it got messed up. So what Marty McFly does is goes back in time and changes what happened, and the future changes, okay? So he debugs the past, and the good guys are good guys again. So when you debug a program, you want to go back in past, find out what went wrong, and fix it, okay? That's sort of the ultimate goal of the debugging enterprise. So the holy grail of debugging is to be able to travel back in time after an error has occurred under realistic operating conditions. That's really key. Of the kinds of errors Jeff Rush mentioned, the most difficult ones are the ones that happen sometimes, the ones that happen to some other people, and ones that happen under load. Those you cannot do in an isolated debugging setting. So you want to do this going back in time under realistic operating conditions. And actually, there are people, especially in Java community, who have done that. They have JVMs which record everything that happens, and they can just, it's like a digital video recorder. You can just rewind it, go back in past, and see what happened, and find out what the source of the error are. But obviously, that only works for small programs. I mean, you'll be overwhelmed with output if you do it in a realistic web server. You couldn't do that. And the same with logging. You could log to find out errors that occur occasionally to other people, but you have huge log files to deal with. So that's the ideal, but it's very difficult to reach the ideal because you have limited memory and limited time to do that. So real-life debugging, one of the hardest things is to duplicate conditions under which the error occurs. So you formulate hypotheses as to where the error is initiated, and then you insert breakpoints and prints along possible error pathways. It's a bit like doing research in science. You have to formulate hypotheses and decide where to instrument your program to find the errors if it's a large program and the error occurs occasionally. And then you rerun it to reproduce the error. That's the real-life debugging. So the current state of debugging is that for interactive programs that perform well-defined tasks, current debugging techniques work very well. You can do PDB, you can trace line by line. And for web servers, especially asynchronous ones, which are used by lots of users, the logging files can be really large, and the line-oriented or stepping through the program doesn't really work if it's a live web server. You couldn't do that. And if you put a breakpoint in an asynchronous web server, nobody will be able to use it because it's often single-threaded. And request processing actually may involve multiple servers. A server might get data from one place, give it to another server, so it's distributed. So if the error propagates, it's very difficult to track it using standard debugging techniques. So this is from Monty Python, if you're not familiar. So the approach I'm going to talk about is it's called OTrace. And what OTrace does is it maps all objects in a running program to a virtual file system. And if you use Unix, it's like the proc file system. The proc file system does it takes strange things and maps them to a file, okay? And it looks like a file system, but it's actually what it's being mapped to is not a file, but you can read from it and you can write to it. So it's similar to that. You can take snapshots when certain conditions occur, like an exception occurs. The snapshot is basically like if you have self that's stored, the objects are stored in the snapshot. And by default, the snapshot doesn't copy, it does a shallow copy of the object. So for efficiency, if you do a deep copy, you can really get into all kinds of trouble, but there's an option where you can do deep copies, but normally just keep the shallow copy of the object when it takes a snapshot, and the snapshot is saved in this virtual file system. And I gave this talk at the Austin Python users group, and they said, if you save this snapshot in memory, and web servers don't have much memory, you'll soon run out of space. And at that time, they asked, can you save the snapshot? And I thought it couldn't be done, but actually, the new version, you can save it. The snapshot can be basically pickled and saved to a SQLite database, so you can reload it later. So it's like a log file, except it's basically a pickled state of the object when it's saved. There's an object shell which looks like the Unix shell, which you can use ls and cd to navigate the objects. And this is this is the feature I use 90% of the time. There's all kinds of other features, but the one I use most is monkey patching of live code when it's running. And what I can do is I can run VI on live code on any function or method and edit it and save it. And it doesn't change the file that the method came from at all. It just changes the method in memory. Okay. And I do that to put print statements, and when I quit the program, the print statements disappear. So I don't have to remember to delete them. And that probably is the most useful feature of this. And the other feature is you can tag objects, you can add a special attribute, and if you have cooperative programs across different servers, then when the object goes from one server to another, then you can debug the object in other servers as well. So the object is tagged. Program is pure Python. It's just one file. It's a pretty big file, but it's just one file that you just import into your program. So commands, there's function tracing. So each function or method can be traced dynamically. The way it happens is it decorates the function. So any function that's to be traced is decorated, and OTrace comes in and grabs and looks at the arguments before it calls the actual function. And if there's an exception, it traps the exception, creates a snapshot before it continues the propagation of the exception. The virtual directories are basically implemented as a list, and you can basically CD infinitely deep into the directory. You'll see that in a moment. You can just keep CDing into a directory. And the way it does is, conceptually, the dir function in Python, it takes any object and lists all its attributes. It's like the directory. And what it does is you can pretend that's a Unix directory, and you can just keep CDing into that forever. You can go around in circles if you like. And monkey patching, the way it does it, it basically gets the function's code from source, changes it and compiles it on the fly, and overwrites the table entry for the function. So that's how the monkey patching is done. And it keeps the original source, so when you can undo that monkey patching as you need to. It'll put the original source back if you unpatch it. So that's the way it's implemented. And so the way you put it in a program is just import this file called OTrace. Typically, you'd use OTrace only when programs that are used by that have an event loop. It's not very useful when you don't have an event loop. It's better off to use PDB. So it runs in its own thread. So it doesn't interfere with the main program, the main event loop. And typically, you run it so that OTrace gets the terminal input, and your web server sort of does the web serving thing, and you interact with OTrace using the terminal. And this is the way it looks. You just insert a line which instantiates OShell, and then you start the OShell loop in its own thread, and then you start the event loop, and then when you shut down, you do a cleanup call. That's basically all you need to do. And actually, a way you can invoke it even without changing the code, just like you use a PDB, you can do that as well. So the object shell looks like this. So you get a prompt. You can do, so when you run OTrace on a program, you'll get a prompt. You'll get a prompt like a shell prompt. And the default directory is called /osh/globals. That's all the global variables of your main program where you call OTrace. And there's a shorthand. There's various tilde G shorthands. Tilde shorthand, tilde G gets you the global directory of the program. Okay. And you can also go to the usual Unix directories. So you can go back and forth within your program and your actual files. Okay. So if you don't have /osh in your path name, it's like a simple shell. Okay, that's the working directory where it's done. So this is, I'll show you the demo program later. When you run the demo program, this is what ls looks like. These are actually the classes and the methods of the main program. Okay. The demo program has these classes and methods. You can say you just want to see the classes. Okay, you don't want to see the methods. You can do -C. These are the classes in the main program. And the objects, so the demo program is called Hello Trace, and this is a snippet from that which shows a global variable request stats and a class get handler which has a do get method. So it's a simple web server using the standard Python HTTP handler. So this snippet is mapped to the following files. So you have global/request stats, globals get handler, and so methods get mapped under the class they're in. So you can just CD into the methods. You can use wildcards just like you use Unix wildcards. Okay, next movie reference is Blade Runner. One of the things, if you've seen it, is that you have these replicants who are trying to remember things in the past, and all they have is snapshots. Okay, so that's what, when you're debugging a program, ideally you want to go back in time and rerun the movie backwards, but typically it's too expensive to do that. But if you have snapshots, you can, at the right place, hopefully, you can go back in time and try to figure out what happened. So when you have an exception that occurs, say in the snippet of code that's shown there, there's a class receive and there's a method respond. When you have an exception, a log message is generated that's shown below. And basically the arguments to the function are saved in the virtual directory. So there's a snapshot of all the arguments. You can just cd there and look at it. And it's there. The way it works is that there's a default of 10 or 100 snapshots that are maintained. It's a parameter that you set. And if you get too many snapshots, the oldest ones are deleted. Unless you pickle them, then they'll be saved in the pickle file. So you need to conserve memory, so only a certain number of snapshots can be retained. But you can just cd to the snapshot and look at the variables, arguments. And this doesn't stop the function. The function keeps running. So you don't, the snapshot just stays in memory. So this works very well with asynchronous programs because the program flow is not interrupted. And anytime you can use cd space tilde tilde, that takes you to the latest snapshot, the latest error condition that occurred. And so these are the things you'd see there. You'd see the call stack. You'd see the variables, the arguments, and typically the self variable, that's the first argument. You'll see that. And so you can cd into self and look at all the variables of the components of self. OK, next we come to printf debugging. This is my favorite technique. I put print statements where I think the error is occurring. And it works always. You don't have to know anything about any language because pretty much every language has a print statement. And the cons are that you have to modify files. I don't like that. Sometimes you forget to take it out. And often produces too much output. You have to put if statements and all kinds of stuff. So the next movie reference, it's Being John Malkovich, where the attic that you see in the movie is like going in and monkey patching the code. You can go and change the code of the program while it's running. Okay. So monkey patch is a way to extend or modify the runtime code in dynamic languages without altering the original source code. It's not necessarily a good programming practice. Apparently some languages do that as a patch mechanism. Here I'm just advocating it as a debugging technique. And what you can do is there's an edit command in OTrace. So in the command line, the OTrace prompt, you say edit, and you give the name of the method you want to edit. It'll start with /osh globals, the class name, and the method name. And it basically opens up an editor of your choice. You could set the editor to VI, you could set it to Emacs. You just go in and only the function you're editing will appear. You won't see the whole file. And then you save it. You just quit the editor and it automatically changes the code. And it saves the original code in a separate directory called patches. So you can go back at a later time and unpatch the code or unpatch all the patches you made. And this is the feature I find most useful, that if there's an error occurring and all the conditions for the error are in place, you can go in and change the code and put in print statements. So this is like breakpoint, except that you do it as needed. And you don't have to edit the source code at all to do that. Object tagging is you can put a trace command and say that when certain conditions are satisfied, like the argument has a certain value, you can add an attribute to the object. And then whenever the object is passed an argument to any other function, then the function automatically is traced. Okay? So the object gets passed around between functions. You don't have to explicitly put, you can just say trace the function only if a tagged argument appears. So you don't tag based on line numbers or function names. You trace based on the condition, like a contaminated object is an argument to the function. And it's just an attribute that's added to the object to indicate that. And the nice thing is that if you have multiple servers handling that object, the object being passed around, if you tweak the code to preserve this attribute, then you could have OTrace running on all the servers, and they would track the object as it passes between the servers. But you need to make the program a little aware of OTrace to do that. So it can be used as a tool for debugging interactive programs. It can be used as a console for monitoring production servers. As I said, OTrace does this by decorating functions. So if you import it, nothing happens until you do the first trace command. There's zero overhead. And it's not like, it doesn't call set trace or any of those things which is executed every time. So it's zero overhead until you actually turn it on. You can use it as a teaching tool. You can go in deep and explore the structure of the code using the cd and ls commands. And OTrace, it can have an initialization file where you can apply patches for testing, and so you can automate it. So you don't actually have to type in the commands on the prompt, because before it runs, it reads an initialization file. It's just like the source command in bash. It can read an initialization file. And you can apply patches only to the code without altering the actual files. And to use it on a live server, you can use it with GNU screen. That's the way I do it. You can start up your server with the screen -d -m -S server name and executable command. What this will do is to demonize screen, and anytime later you can go to see OTrace output from the server using the screen -r command. So the server can be running in the background, but you can just connect to it and invoke OTrace and basically do live debugging using this. And the moment you start typing trace command, that's when the decorators are added to the code. And that's when you could have some overhead associated with it. I mean, in principle, you could patch the code and crash it. But until you do that, there's no danger of having OTrace in the code. Have we reached the Holy Grail? It's not a back-in-time debugger, but it does snapshots in memory. So it's sort of an approximation to that. And you can pickle the snapshots, so you can store, to the extent you can store the database files, you can save the snapshots. And you can keep it on in production systems. So it's similar in philosophy to dtrace. And there's no performance penalty until it's used for tracing. And I'm going to go into the demo portion now. But the talk I gave at 8 o'clock was about a graphical terminal interface. Actually, it was developed to serve as a GUI for OTrace. OTrace can be used perfectly fine with the command line. You don't need the graphics for it. But this can be, so you can do remote debugging with this using the browser. So you can, the browser can connect to the command line, and you can debug your program from a different computer using just the browser. And what happens when you use GraphTerm is like the ls output, which lists the classes as functions, it becomes hyperlinked. So instead of doing cd ls, you can just click on where you want to go, and it'll automatically take you to the part of the program which you want to look at or modify. So this is not the end yet, but the best way to show you how this works is to show actual screen, live screen of how this works. And once we get towards the end, I'll stop. Actually, I can stop here for quick questions, and we can have more questions later. Any questions so far? Okay. Let me quit this. Okay, so what I'm going to do now is run OTrace on the demo program. Also, this is the directory you'll see if you download OTrace and go untar it and look into it. This is exactly what you'll see. So I'm going to run. Okay, so I'm running this demo program. And what this demo program does is computes the reciprocal of a number. Okay, so I'm going to fire up the web server and show you the demo program running. Okay. So the demo program, it takes a number from the user and it computes the reciprocal of the number. So if I type 2, it does 0.5. And obviously the program can fail if the number is 0. And the way the demo is written, it will not detect 0. So it's going to fail if I type 0. So I'm just simulating an error in the web server. So I'm going to type 0. So you get an exception occurring. So this is sort of a typical error. I mean, it doesn't have division by 0, but an error that occurs occasionally for some people will trigger an exception. And let's see how OTrace will deal with the exception. By default, it doesn't do anything. So if you look at the console, you just see the standard error message from Python, which says that there's a float division by 0. So what I'm going to do next is trace. I'm just going to remind myself of the demo, and I remember exactly what the demo involves. Okay. So this is the documentation. So I'm going to So I need to trace the function called receive.response. I'm going to do that. That's the one that's causing the error. And then let me repeat the So I'm going to reload the page and then create the error again with the trace enabled. Okay, so now the difference is the function was being traced, so the decorator caught the exception. And what you see before the float division by 0 message is the log message from OTrace, which says that it's a 0 division error, which is an exception. To get to that snapshot, I do cd tilde tilde. So now I'm in the snapshot directory, and you can see what that is. If I did pwd, I'm in the directory which is named recent exceptions. So every time there's an exception or a different kind of error, there's a directory which describes the error and a sort of a timestamp thing that tells you when the error occurred. The last few digits are the time when the error occurred. So you can have a sequence of errors occurring. So we're in that directory. If I do ls, you'll see information relating to the snapshot. There's a trace, there's up that lets you go up the call stack. Request is one of the variables in the function, and self is the sort of the instance that the method is associated with. So I can do cd self, let's say ls. So it has two attributes, respond and value. I can see what they are. So respond is a method, and value is a number 0. So it's a number 0 you typed in on the web page, and so the method respond created the error. So this is how you track errors in OTrace, and let's go back to the main directory. So if I say td tilde tilde g, if I say ls, I'm at the root of the program, so I can go to cd receive. So you can use tab completion, just like you do in a shell. So I'm in the function right now. Okay? So if I actually want to look at the source code, I go up one directory, and I say view. I want respond. So this is the source code for the function, so I can just do a view command, and I can look at it. So you see that the two arguments are self and request, and it basically computes a reciprocal at the last line, and that's where it failed. So what I'm going to do now is to patch the code live. So I use the edit command. Before that, I have to do something called set safe mode, because normally it won't let you patch it by default, so you don't mess it up. Okay, now let me patch it. So what I'm going to do is, instead of viewing the function, I'm going to edit it. So now I'm in VI, and I'm looking at the source code of the function. And what I'm going to do is, I already put in the modification I want to make, the commented out. But in principle, you can type in anything here. And I can't see it. Oh, I'll do it here. So I'm going to comment out these lines. So what these lines do, the two sets of lines are commented out. They're going to detect if the number is actually less than 0.001. They'll detect if the number is less than 0.001. The first two lines will print a message. And the second two lines, they do what's called a trace assert. So it's like the normal assert in Python. So if the condition is true, nothing happens. But if the condition is false, it triggers OTrace snapshot. So you can snapshot not just, similar to a breakpoint, except it's an assertion that's traced. And so the first argument is the condition. The second, the associated label that with the snapshot. So if I run it now, the program will detect if the number is less than 0.001 and automatically trigger a trace snapshot. So I'll do that now. So I just quit VI, and now the method has been patched live. So let me run. I'm just going to run the server again. So now I'm going to type in, let's say 2. Nothing happens because the number is fine. But if I type in 0.0005, that's less than the threshold I put in. The program ran, but if you look here, there's a log message which says num check trace. So that was the label I put in the patched code. And I can just do cd tilde tilde. So this shows you the snapshot associated with the trace assertion failure. And again, you can look at the So you can look at the values in the variable in the snapshot. So the value is 0.0005. So you can actually do, if you have a hypothesis as to where the error is occurring, you can go in and patch the code, put in any kind of change you like. And if you're done with the patching, what you do is you go back up to the top level. So there's a top level directory. So you have globals, locals, patches, pickled, recent, and saved. Globals and locals are basically a globals and locals dictionary for the program. Patches is all the functions you patched. There's a link there we'll see in a moment. Pickled is if you pickled your snapshots, you can retrieve them and they'll appear in pickled. Recent is all the recent snapshots that have happened. So you can CD to those. As I said, there's a limited number, and once there are too many snapshots, they get moved. Actually, there's one more called all. They get moved to all. And there's a weak reference in all. So as soon as you lose memory, those things will disappear. But if you move the snapshot to saved, then they'll stay there forever. So if there's a snapshot you want to look at and you don't want it to disappear, you have to move it to saved. So let's look at patches. So received or respond was the method I patched. So there's a record of that here. And I can do so now the function's been unpatched. So the patch applied has been removed, and there's nothing more left in patches. So when you're done with your patches, you can go ahead and basically unpatch it, or you can just quit the program, then the patch will disappear. If you look at recent, so two kinds of conditions have occurred. Assert failures occurred and exceptions have occurred. So if I do that, so this is all saved in memory. And so the assert failure occurred in the function receive.respond. And the label that it had was numcheck. So I can go to, and the time it occurred. This is actually very important if you're debugging web servers because you get a sequence of errors happening. And that's a date and the time up to seconds. And actually, you'll even go to milliseconds if there's ambiguity. So if there's several snapshot with the same second value, you'll start adding the point or something to it to distinguish between them. So if I go into so this is what the trace snapshot looks like. And if I can go to oops, the double and like this. So if I type where, it tells me where exactly this trace occurred, the call sequence. And you can see the last element entry there is respond, where the trace occurred. It was called from the method doGet, which is called from handle one request, which is called from handle, and it just goes all the way back up to the top. So there's a frame stack, and there's various other things that you can look at. Like one way to look at all the values in a directory, you say ls minus l. ls minus l here, instead of, it's not like the Unix shell one. Here it actually prints the value of each attribute. So you can see all the attributes in the current directory by doing ls minus l. So you can see the ID of the trace and all the arguments that the function had or the trace assert had. So next, I'm going to do one more feature that involves a chat program. And let me try it. I'm going to run that remotely. Okay, it is running remotely. Let me. I don't know if you can see it. It's not the best program. It's actually the chat program from the Tornado web server demo. So I'm actually running it on, if you have a computer, you can actually try it out. So that's what I meant by, if you want to type in the top URL, you can type it in, and we can actually chat, and we'll see what's going on. The URL is OTrace. I don't know if you can read it. It's otrace.graphterm.net:8888. It's 4 8s. I don't know if I can make this any bigger. Well, I'll type in the URL. Okay, people have managed to get in. So this is a live chat program running, and some of you, if you download the Tornado demo, you'll see it. I just made a few changes to it. So what I'm going to do now is running on a public server, and OTrace is running on it. Okay. So what you're seeing is the OTrace output for the program you guys are all chatting on. And it has a feature which I didn't mention earlier. These are all the messages from the web servers people are getting on the chat. So I go to /OSH. There's a new directory here called web, because there's WebSockets here. And these are all the users that are chatting right now. It appears as a directory, okay? So you can see everybody's name there. So what I'm going to do is to CD into one of the users. Let's CD to Doug. You can CD into anything. That's the philosophy of OTrace. It could be an object, could be a function. It just applies the dir function on it and just keeps going. So you can go in circles. So now I'm in Doug's browser. I don't know who Doug is, but but the thing is now I can no longer type shell command. I can type JavaScript. Okay. It's like your. So I'm going to type. I never remember this command. Let me look it up. It turns your background red. I'm going to do that right now. I think I remember it. Let me just hold on a moment. Let's try to find the. Yeah, I'll just copy paste the command so that I remember it. This is the command I need to paste. Yep. So change the background to red. Let's see if that works. Did it work? Your background's red? Okay. But again, this is nice because if you're debugging a program running on an iPad, it's not very easy to do that. So this will work on your iPad. So if you, all it does is it takes the command line you type in, it sends it across WebSockets there, and there's like 10 lines of code that executes the command as the JavaScript. That's all. It's only a few lines of code that does that. Okay, the other thing I can do is, let me type in the other one. The next command is actually, let me type in this one. Okay. Okay, Doug, can you type something? Actually, what this is doing is a repeat command in OTrace, which repeats any OTrace command like every 5 times a second. And it does jQuery on his input element, and it does a .val and just outputs that. That's all it's doing. It's like 2 lines of code. And basically, you can check exactly what's going on in the browser real time. Okay. So this is actually in the command line. So I'm going to Control-C out of that. think I control-C the chat server. Let's see. Let's see. I'll start it up again in case you guys want to chat. But anyway, I think it's time for me to stop. As I said, I really want to do a live demo because it's not the usual thing you see in debuggers. So I'll take any questions. If you want to type any command in the OTrace, you can do that as well. And actually, the server you're going there is public. You can actually, login restrictions. You can actually try it OTrace directly. If you want to do that, well, only one person can do it at a time, so it's. But anyway, I'll take questions. Any questions? Yeah. I've heard this thing that for something to be in standard library, a module, it has to have one foot in the grave. It makes a lot of sense. You don't want to change it. That's the whole thing, because it'll break everybody's program if it's changing. So it'll take time, perhaps. But it's just one file. It's about 4,000, 6,000 lines of Python. And you can just import it, and so. And I've checked it with Python 3. It runs, but I've never actually seen that it works. But the demo works. So it should work with Python 3. But it's, as I said, there are all kinds of features, but the one I use most is I go in and edit my program. And the reason I actually built the monkey patching feature is I said I have an application that I use to interact with students live. I have 25 students, and I was trying it out, and they were logging in, and the program was failing. And there was just one line. There was a typo in the program. And I thought, if I'm going to fix it by rerunning the server, I'm going to have to make them all log out, log in again. It would be nice if I could just go in and VI the file, the function, remove the typo, and just run it again. You can do that. So it's pretty transparent. It's just like using your shell. But yeah, I don't know if it'll go in the standard library, but it's one file. You can download it and use it. Not many people have used it, so I'm really interested in feedback. And I've used it to debug itself. That's an interesting thing. And it sometimes works and sometimes goes in an infinite loop. You can imagine. But you can actually do CD into OTrace when you're running OTrace, because but most of the time you can do it, but sometimes you keep calling itself forever, and because there's no boundary between itself and the rest of the program. You could build that in, but right now that's the way it is. Anything else? Well, thank you. And if you can download it, try it out, I'd appreciate feedback. As I said, it's not probably for the beginner user, because if you're debugging a simple sequential program, you don't need this. It's more when you're debugging distributed programs, asynchronous programs, or errors that occur only under load, or sometimes that's when you'll need this.